Lesson 6, Advanced Integration Techniques, Recurrence Formulae, Part 2. Example 1. If In equals the integral between pi upon 4 naught of 10x dx for n greater than or equal to 3, show that In equals 1 over n minus 1 minus n minus 2, In minus 2. Hence evaluate I5. Okay, we'll start off with splitting this up. So In is equal to integral pi upon 4 naught, and we'll do the tan n minus 2x tan squared x dx. Now we're not going to use parts. We're going to do this bit. Pi upon 4 naught n minus 2x, and tan squared x, as you know, is going to be sec squared x minus 1. And by doing that, we'll write this as pi upon 4 naught, and that's going to be sec squared x, and I'll write this as tan x to the n minus 2 dx minus, and of course this is going to be In minus 2. But you can see here that this is the derivative of what's inside the brackets there. So all I need to do is increase this by 1. Oops. There we go. Bring it back. So that becomes the tan of n minus 1x over n minus 1 between pi upon 4 and naught minus In minus 2. Now the tan of 45 is 1, and 1 raised to that power is 1, and of course the tan of naught is naught, so that simply becomes 1 over n minus 1 minus In minus 2. Okay, now, so we're going to find I5. Well, I5 is going to be 1/4 minus I3, and I3 is going to be 1/2 minus I1. Now I1 equals the integral of tan x dx between pi upon 4 and naught, which is minus sin x on cos x, with a minus at the front, dx, which of course is equal to minus the log of cos x between, has to be pi upon 4 up here, pi and 4 and naught, which is, now I can reverse these signs and write there's the log of cos x between naught and pi upon 4. Log of, this is the log of, the cos of naught is 1, the log of 1 is naught, so it's going to be equal to naught minus the log of, and the cos of pi upon 4 is 1√2. Of course that simply becomes the log of √2. Right, so I3 must be 1/2 minus the log of √2. So I5 equals 1/4 minus this, that's minus 1/2 plus log of √2. So the final answer is the log of √2 minus 1/4. Example 2. If In equals the integral of x to the n e dx dx, show that In equals xn x to the power n e dx minus n In minus 1. And hence evaluate the integral between 1 and 0 of x cubed e to the x dx. Okay, this is a fairly straightforward one. Let's have a look at it. So I've got my in equals x dn e to the x dx. Now, I'm going to use my integration by parts formula. U dv equals uv minus integral of v du. Okay, so this time I'm going to let my u equal x dn and my dv equal e to the x. So my du equals n x to the n minus 1 and my v equals e to the x. So in must be equal to uv, which is x to the n e to the x minus the integral of, this will be v du, which n goes at the front, and that's x to the n minus 1 e to the x dx. And of course that is your in minus 1. And that's what we had to show back there, right? Okay, now we're going to work out what I3 is, don't we? So I3 is equal to the integral of x cubed e to the x between 1 and 0 minus 3I2 and of course when you put the 1 in there, you're going to get, there's going to be e, and of course putting 0 in makes that 0, so it's 0 minus 3I2. I2 is going to be equal to x squared e to the x between 1 and 0 minus 2I1 which is again e minus 2I1. I1 is going to be x e to the x 1 and 0 minus I0. Okay, and that's going to be equal to e minus I0. I0 is equal to the integral of simply e to the x dx between 1 and 0, which is e to the x between 1 and 0, which is e minus 1. So I1 equals e minus 1, which is just equal to 1. Here I2, which is e minus 2, and I3 equals e minus 3 times e minus 2, which is e minus 3e plus 6, which is 6 minus 2e.